Hello, welcome again. We are solving GATE 2020 Aerospace Engineering paper. Question number 39 is an oblique choke is inclined at an angle 35 degree to upstream flow of velocity 517.56 meter per second. The deflection of the flow due to this choke is 5.75 degree and the temperature downstream is 182.46 Kelvin. Assume the gas constant R is equal to 287 joule per kilogram per degree Kelvin. The specific heat ratio gamma is equal to 1.4. Specific heat at constant pressure Cp is equal to 1005 joule per kilogram per degree Kelvin. Using conservation relation, the Mach number of the upstream flow can be obtained as round up to 1 decimal place. So this is your shock wave and this is the velocity 517.56 meter per second, and this shock wave is inclined at 45 degrees. Okay, so we can resolve this 517.56 into component. One is tangential component along the shock, that is shock wave, sorry, 517.56 435, and other is perpendicular to the shock wave, that is 517.56 sin 35. Okay, now in oblique choke the tangential component remains same. Okay, so velocity along the shock wave is this and will remain same. Okay, so Vt1 is equal to Vt2, but the shock occurs at this across the shock wave. Okay, and this component changes, and now changes due to this the deflection of the shock wave occurs, that is so sorry, deflection of the velocity component occurs. Deflection is 5.75 degree, and this is your the deflected velocity direction. Okay, so now we have Vt1 is equal to Vt2, so this is your Vt2, and now the angle between Vt2 and this deflected component velocity is 35 minus 5.75. So Vt2 divided by cos 35 minus 5.75. Okay, so that will be the V2 or velocity in this direction, and sine component will be your normal component of velocity. Yes, this is your Vn1, this is your Vn2. So Vn2 will be your Vt2 by cos 29.25 into sine 29.25. Okay, because this normal component of the shock changes, sorry, of the flow changes, but the tangential component remains same. So new normal component is Vt2 by cos 29.25 into sine 29.25. Okay, so putting the values of putting values, we have Vn1 as 517.56 sine 35. So this is your, and this will come out as 296.86, and Vn2 as V2 is your Vt2 is your this 517.56435, and putting the value here sine 29.25 by cos 29.25, that will be 237.429 meter per second. So the velocity after the shock will be normal to the shock wave will be 237.429, and before shock it is 296.86 meter per second. So now now across shock the energy equation is satisfied. So we take the energy equation, that is H1 plus Vn1 square by 2 is equal to H2 plus Vn2 square by 2. So as Vn and Vn1 and Vn2 are known, and the temperature of the shock is also known, that is 182.46. So we can find out H2, and then we can find out temperature before shock by putting H1 as CPT1. So T1 comes out as 166.66 Kelvin, and the velocity before shock is 517.56, and sonic velocity is this 1.4 287 and 166.6 root. So the Mach number before shock comes out as 1.9. Answer is 1.99. Next, the thickness of a laminar boundary layer delta over the flat plate is delta by x is equal to 5.2 REX, where X is measured from leading edge along the length of the plate. The velocity profile within the boundary layer is indicated, is idealized as varying linearly with Y. For free stream velocity of 3 meter per second, the kinematic viscosity of 1.5 10 to the minus 5 meter square per second, the displacement thickness at 0.5 meter from the leading edge is dash and round up to 2 decimal point. So delta by x is your 5.2 by root rex. So x is your 0.5 meter. Okay, and rex is your bx by mu. B your 3 meter per second and mu is 1.5 into 10 to the minus 5 meter square per second, and x is your 0.5 meters. So rex is your this 3 into 0.5 divided by 1.5 into the minus 5, or it comes out as 10 to the 5. So from this relation we can find out delta at x equal to 0.5. So it will be your 0.00822 meters. Now the velocity profile is given as it is given that the velocity profile is linear. So it means that the velocity profile is like that, u by u infinity by delta. For displacement thickness, we know that it is the integral of 1 minus u by u infinity dy with limit delta to 0. Okay, so putting the value of y by u by u infinity, that is y by delta, and then indicating that will be y minus y square by 2 delta and delta 0, or it will be delta minus delta by 2, or it will be, now delta is 0.00822 by 2, so that is 0.00411 meters, that is 4.11 mm. Okay, so answer is 4.11 mm.